Okay, please start.
Okay, thank you very much, Professor Kamada, for that introduction. And thank you very much to the organizers for the invitation to be here. I'm very honored to be here to celebrate the 80th birthday of Professor Luke Hoffman. Just going to show you this. I took a screenshot of one of the first papers that I ever read as a graduate student, and I imagine that many of you are familiar with this paper. It's the Kaufman bracket paper. And so I was very excited to learn about all of this, and even more excited when I would travel to these Knots in Washington conferences that everybody could speak at when I was a graduate student and see someone who I considered to be a celebrity. Luke Kaufman was a fixture at the Knots in Washington conferences, and I gathered still is. So, um, as I said, really happy to be here to celebrate his birthday as part of this conference. And thank you all for coming to this talk. It's 7 a.m. in Lincoln, Nebraska. I don't see my office at 7 a.m. on a Sunday very often, but I happen to be organizing an undergraduate conference this weekend, and it doesn't start today until 8, and so the timing worked out perfectly for me. Okay, so I want to tell you a story today about the ribbon numbers of ribbon knots, and the coffin bracket will come back later. So maybe I'll say something controversial. It's a good way to start a talk, right? This thing that I just drew, this is not a knot. You see it and you picture a knot. We're all three-dimensional beings, and so our mind makes that three-dimensional. But this thing, this is a knot diagram. Oh, I better did KNOT. There we go. I'm still waking up here. This is a knot diagram, and you're like, oh, you're being pedantic. Of course, there's knot diagrams and there's knots, but we seamlessly go back and forth between these things, and it's not unless someone says we're doing something with diagrams that many of us sort of like recognize that indeed we're thinking about this as a two-dimensional projection of a three-dimensional thing. So knots live in S3, and knot diagrams live in the plane, or if I'm compactifying, maybe knot diagrams live in S2. All right. And so in the same way, let me draw, oh no, I'm going to show you a picture. A ribbon disc. So this is a nice ribbon disc that one of my undergraduate students 3D printed for me. So hopefully you can see the, oh, I have it somewhere. Here it is. I could have just shown you up there too. Here's the ribbon disc. So of course the knot is the edge of the ribbon disc. But I will make the same statement. This is not a ribbon disc per se. Okay, this is what I will, at least for the next 5 minutes, call a ribbon disc diagram. And the reason I'm making this distinction is that for people who haven't thought about ribbon discs before, there are two accepted definitions, one in dimension 3 and one in dimension 4. And this can be very confusing for people new to ribbon discs because how can those be the same thing? So what do I mean by ribbon disc diagram? A ribbon disc diagram is an immersed disk in S3 with only ribbon singularities. So it can intersect itself, but the self-intersections aren't so bad. So what does a ribbon singularity look like? Locally, I have two strands that pass through another piece of the surface like so, and here I'll color in the surface like that. So it has these ribbon self-intersections, and in this 3D print, you can see them right here and right there. And of course, the knot K is the boundary of the disk in this case. So it's a ribbon disk diagram for a knot. So then if this is what I mean by ribbon disk diagram, what do I mean by ribbon disk? A ribbon disk is an embedded disk in the four ball B4 uh, with only minima and saddles, but no maxima with respect to the radial Morse function on the four ball. And so I'm not going to draw any four-dimensional pictures as part of this talk. For people who are newer to the field and haven't seen this definition before, just think that it's something that lives in four dimensions, something embedded. The key takeaway here is that a ribbon disk diagram is contained in the three sphere, whereas a ribbon disk is contained in the four ball. And so there's this analogy between knots and knot diagrams as I go back up here. Oh, I did it in the wrong order. Let's move it over so the analogy is better. I'm going to strengthen this analogy by geographic placement on my screen. Okay, now I can highlight things. It'll be great. Okay. Knots live in S3. Ribbon disks live in B4. Knot diagrams live in S2. Ribbon disk diagrams live in S3. Okay, and now I'm going to do something which is, could be upsetting because you're like, oh, I like this analogy. I haven't seen this distinction before. I'm going to follow convention, and convention is we call both of these things ribbon disk. So I will never say ribbon disk diagram again in this talk. We abuse the definitions and just call it a ribbon disk. They're both ribbon disks. And I think the reason that we often do this is that people aren't used to thinking about the disks. People think about the knots. So K is called ribbon if K is the boundary of a ribbon disk. And so if you are just thinking about ribbon knots, this subtlety doesn't matter because it's both the same. If I bind a ribbon disk diagram, I can take that and there's a bit way to perturb this into the four ball to get a ribbon disk of the four-dimensional variety. And conversely, if I see a ribbon disk of the four-dimensional variety, I can project it, I can push it into S3, and I can get this immersed disk with ribbon singularities. But one subtlety is that there are different ways to do this. So for instance, when I push my four-dimensional ribbon disk into S3, I could do something like this. So let's see here, like that and like this. Okay. So I can do something that kind of looks like the more complicated part of a Reidemeister 2 move, where I push a piece through another piece. And so I can get different projections of the same ribbon disk, just like I have different diagrams of the same knot. And this talk is about understanding these number of ribbon intersections. Okay, so let's define this. The ribbon number of a ribbon disk. And hopefully it's clear from context which version of ribbon disk I'm talking about, but I can state that this is for a three-dimensional ribbon disk for the projection. Let's call it D. So let's see, the ribbon number, let's name it right there, R of D, of a ribbon disk D, is the number of ribbon intersections in D. So for example, if I go back up to my picture of the ribbon disk for, this is the square knot, by the way, there are two ribbon intersections. The ribbon number of this disk is 2. And just like with something, like the knot genus, we can turn this into a knot invariant that is hard to compute by taking the minimum overall possible presentations. So that's the ribbon number of a disk. The ribbon number of a knot K, we'll call this R of K, is, we just minimize. It's minimum of R of D, taken overall ribbon disks D, such that K is the boundary of D. And, I guess you might say, wait a minute, not every knot has a ribbon number. Of course, not every knot is ribbon. And so I maybe we'll say R of K is infinity if K is not ribbon. I'm not too worried about non-ribbon knots. But that's a knot invariant. Of course, it's easy to construct a knot invariant in this way because we've artificially declared it invariant by minimizing over some infinite search space. And this leads us to a question, which is, can it be computed? Yeah. So perhaps I will say that we did not invent this invariant. Oh, I didn't even acknowledge my collaborators yet. I'll blame that on 7 a.m. Let's do this now. So this is joint with Stefan Friedel. Not Friedli. Friedel. Philip Misev. I'm going out of order because there's one paper that's joint with Stefan and Philippe, and then a second paper which is joint with Jeffrey Meyer, and then Evan Scott, and then a large team of, oops, no comma between Evan and Scott, a large team of undergrads, which I will mention all of them by name at the end of the talk when I roll the credits. Okay, so my collaborators and I did not define this invariant, but it was relatively um, unexplored in the literature. And so the first definition we can find in the literature is in a paper by Yoko Mizuma. So this is a theorem from 2006 of Yoko Mizuma. And this person just wanted to know if they could compute the ribbon number of the Kinoshita-Terasaka knot. So the theorem is that the ribbon number of the knot 11 and 42 is equal to 3. And there's a story there, but that was the first place that this was explored. If you go on MathSciNet or the archive or anywhere else and Google ribbon number, you will find references to ribbon number earlier than 2006, but some folks called something that's now called fusion number ribbon number. So maybe I should write that. Some earlier references to ribbon number are in fact talking about fusion number, which is a different complexity of ribbon disks. It's related to the disks and the bands. The fusion number counts how many bands you're using in your disk presentation. Okay, so back to this question. Can it be computed? And, maybe the question that Stefan Friedel first posed to me, I was visiting him, he invited me to visit, and we're sitting at the bus stop, and we're kind of just ruminating on math as these things go. And he said, can you find lower bounds for the number of ribbon intersections of ribbon disks? So are there, of course, when I say, can it be computed, it is like most invariants of this type. It's easy to find upper bounds. You just pick your favorite picture and you have an upper bound. But the tricky thing is the lower bounds. So are there effective lower bounds? And, if you'd never thought about something like ribbon number before, which I think is probably most people in the audience, you could sit and chew on it for a little bit, and you would realize that knot genus is the first thing most people think of. Knot genus is a good lower bound. Let me show you a picture that will convince you. So the answer is yes, and this was observed in papers before ours. I don't know if it was first observed in the Mizuma paper, but it was first observed. Probably it was in there. So yes, the 3 genus, and the picture that is meant to convince you of this is, let's pull it up right here. I got it right here. So this is a resolution of a ribbon intersection. If I zoom in on a little piece of my ribbon disk, what I can do is take a pair of scissors, snip open the ribbon intersection. I imagine now cutting open the blue sheet of the surface like a trap door, folding one piece up and folding one piece down. and affixing these little red tabs. And what I've done is turned an immersed surface into an embedded surface. And so a ribbon disk with ribbon number equal to G via this process, if I resolve all the ribbon intersections, I can end up with a ciphered surface of genus G. And some of you are saying, wait a minute, that surface you might have gotten could be non-orientable. How do you know that the orientations, the normal orientation of the blue sheet matches the red sheet and you haven't made a non-orientable surface? And so yes, absolutely. The thing is that this trap door, I can open it this way or I can open it the other way. I see, I see the drawer has pulled up a separate picture. So there's another picture of this. In any case, there's always an orientable and a non-orientable resolution. And if you choose the orientable resolutions, you can construct a ciphered surface in this way. And so if I have a ribbon disk with ribbon number G, I can find a ciphered surface with genus G, and that immediately tells me that the ribbon number of a knot is bounded below by the genus of the knot. So there's an elementary lower bound, and you might say, how good is this? And it's pretty good for a lot of knots. This is effective for what we call generalized square knots. So QPQ is the TQ torus knot connects on its mirror image. And the ribbon number is equal to the genus for these knots, and the genus, well, ribbon number of QPQ is equal to P minus 1 times Q minus 1. And there's a lovely construction of these surfaces. And so it works out really nicely for some knots. But maybe our aspirations are higher than this. We want to tabulate as many ribbon numbers as we can. Okay. And so the next thing we found was a theorem of Yasuda. And so maybe I'll make a remark here, is that while ribbon number has received relatively little attention, it's closely related to something called the ribbon crossing number of ribbon 2 knots in S4. And I don't want to really go into detail here. Maybe I'll say in words. If you have a fusion diagram for a ribbon 2 knot, you can count how many times the 1 handle is crashed through the 0 handles, and then you minimize that overall presentations, and that's the ribbon crossing number. And in fact, if you take your ribbon disk in S3 and you double it, you can get an immersed surface a broken surface diagram for the ribbon 2 knot, and the ribbon intersections each give you a crossing, and so these are really closely related. And so it's not too difficult to take theorems that were meant for ribbon 2 knots and translate them in some way to the setting of ribbon numbers for classical knots. And so we found this result of Yasuda, and maybe I'll write it like this. Theorem of, so Yasuda's theorem was for ribbon 2 knots. And I'm going to put our names here because we did the translation, but the real work is in Yasuda's theorem. But I don't want to state Yasuda's theorem and then state our result as a corollary because it'd take too much. So I'm just going to state it as one theorem, which is that, well, even a corollary of this, it says something about the coefficients of the Alexander polynomials. But the takeaway is that if K is a ribbon knot, then the determinant of K is a lower bound for, not quite the ribbon number, but this function of the ribbon number, 2 to the ribbon number K minus 1 squared. And this is also effective for a large class of knots. So now we're getting somewhere. I mean, the natural question, right, when you find one obstruction, you say, okay, among all knots for which that obstruction doesn't work, can we find another obstruction which does work? So you can find, for instance, now genus 1 knots whose ribbon numbers are unbounded as a family. And so now, okay, can I find genus 1 determinant 1 knots whose ribbon numbers become unbounded? That's the next thing to do. Yasuda's theorem actually does give us that as well, with the stronger statement about Alexander polynomial. But let me shift gears and tell you about ribbon codes, which is something we use to do some enumeration here. Okay, so every ribbon knot has a disk band presentation. And let me say this for disks. I mean, the knot is the boundary of the disk, but every ribbon disk can be built with disks and bands. So I start with a collection of embedded disks, and then embedded bands, which I'll call B, that meet the interior of the disks D. And this is the kind of thing that I'll just show you an example, and that'll be sufficient, hopefully. Okay. So here's two different ribbon disks, and they've been divided into these blue regions and these pink regions. And so you can think of the blue regions as being two disks, and then I attach a band, and this band has like opposite edges glued to the disks, and then along the band I can crash through the interior, and this is precisely where my ribbon intersections happen. Okay, so every ribbon disk can be broken up in this way. And if you do like thinking about the four-dimensional perspective, this also tells you it's a choice of minima and saddles with respect to that radial Morse function. You can build the four-dimensional picture where the minima correspond to the disks, and then the saddles correspond to these bands. They give you saddle points. And then once you attach the bands, that's like passing through the saddles, and then the knot becomes the boundary of this disk after the band attachment. And so there are two examples, and let me throw in one more. I think I have to shade this one a little bit. Yeah, let's put this, we'll put it right here. So this one isn't quite so clearly broken up because I didn't do the shading yet, but oh, I guess I should do the bands in red. So here is a band right there. Here's a band there. And so the thing in the middle is also one of the disks here. So this is a disk band presentation for a disk with 4 disks and 3 bands. And now I want to show you how we can extract some information here. Well, let me tell you a problem. So here's a problem, an issue, an obstacle, because my intuition, the heuristic we were working with was thinking of these things as like thinking of ribbon number, excuse me, as like a crossing number for ribbon disk. It's not a perfect analogy, but you project something and you count self-intersections, it feels like crossing number. How do we find the crossing number of the trefoil? Well, we simply find a 3-crossing diagram and then enumerate everything with 2 or fewer crossings. It's interesting for an undergraduate student to do as like a first exercise to prove that the crossing number of the trefoil is 3. We just exhaust it. And we can, in theory, do this for crossing number, 20 if we have enough time and computing power. So the problem here is that there exists infinitely many ribbon disks with, for instance, ribbon knots. Ribbon disks as well, but there are infinitely many ribbon knots with ribbon number equal to 2, or for any ribbon number k equal to n. It turns out that you can't have a knot with ribbon number 1. If you have ribbon number 1, you can prove that fusion number is 0, so that knot has to be the unknot. But in this picture, we see that, I can take the band, I can add full twists, I can add half twists if I wanted, I can take the band and like pass it through itself and tie it up. I can do all kinds of different things to the band without affecting the ribbon number. And so there's no hope of exhaustion. I can't just say, okay, I'm going to enumerate all these things, and then this isn't in my finite list, and so I move on. But what we can do is pass to some information that ignores these things, ignores twisting, and ignores the homotopy type of the bands, and that's called a ribbon code. And so I'll draw you an example. So the ribbon code is a graph. The vertex set corresponds to the disks. The edge set corresponds to the bands. And then there are some markings. And so I'm going to put two markings here, and those correspond to my ribbon intersections. And I will label them
Can you
to,
scroll a bit?
sorry?
Can you scroll a bit? What you're writing is not showing.
Oh, it's not showing? It's showing on my screen. That's interesting. It's right below the disks?
It's just tiny.
Oh, it's too tiny. Okay.
Sorry, it's okay.
I will write slightly bigger. I'm sorry about that. So this one we'll label as 2, and this one we will label as 1. Is that a reasonable size? Okay. And the labeling is the band passes through disk 2 first as I travel from disk 1 to disk 2, and then it passes through disk 1 second. And there is a sign convention, which I don't really want to take the time to discuss, but these can have a plus or a minus sign depending on how the band passes through the disk. Okay, let me move this disk over and make sure that I try to write large enough. So this one has, I got to label these. Here's disk 4 and 1, 2, 3. So I have 4 vertices and 3 edges. And if I label the vertices 4 and 1 and 2 and 3, now technically the band from disk 4 to disk 2 is this band, and that crashes through disk 1, and so I will put a marking right here and label that as 1, and then this marking is 2, and this marking is 3. And so this is a ribbon code. And so a ribbon code, let's make it in black. A ribbon code is a marked graph that encodes the combinatorics of a disk band presentation and its intersections. So that's what a ribbon code is. And so now I can solve a solution to the problem is in the following proposition. So a couple of bullet points. So given some integer n, there are finitely many possible ribbon codes with ribbon number equal to n. The ribbon number is the number of markings in the ribbon code. And you might say, wait a minute, I can make this really long string with no ribbon intersections, and that's a different ribbon code, and I can make that as long as I want by kind of dividing a band up into disks and bands. And so finitely many possible, I'm going to put in a word here, I will not define it. There's a way of simplifying ribbon codes if you see silly sort of stuff that someone has introduced that you can just cancel. So there are finitely many possible irreducible ribbon codes. That means you can't make it any simpler with generic moves. Okay, so that's one bullet point. The second bullet point is that the ribbon code uniquely determines the Alexander polynomial of the corresponding boundary. If I had a bit more time, I do want to talk about the Kaufman bracket though, so I'm going to skip over the verification of that fact. But that is a less elementary fact, but still something that I'm sure many graduate students could do as an exercise if they wished. So you take a ribbon code, and that's enough information to find the Alexander polynomial. And therefore, if I define the set R sub n to be all of the possible Alexander polynomials of knots such that the ribbon number of k is less than or equal to n, well, I have finitely many inputs, and I'm computing finitely many polynomials. So this set is finite. So despite the fact that I can find infinitely many ribbon knots with a fixed ribbon number, the realized Alexander polynomials of those ribbon knots live in some finite set. And that set is computable. So one thing that we proved, this is Friedel, Misev, and myself, is that there are only 3 polynomials in the set of all knots with ribbon number at most 2, and there are only 10 polynomials in the set of all knots with ribbon number at most 3. And then the theorem with Jeff Meyer and Evan Scott and lots of undergrads, which I will just call Polymath Junior. This is the result of a massive open online REU project that we led in the summer of 2023. The paper came out in 2024. Anybody who supervises undergraduate students from anywhere in the world should consider, I'm just going to write my plug for the Polymath Junior REU. This is an open access REU, which has hundreds of students participating every summer. There's no stipend or credit given for this, but the great thing is that you don't have to be a US citizen. You can be anywhere in the world. As long as you're an undergraduate, you can apply for this program, and almost everyone gets in. So the downside is that there's a lot of people working with one mentor. I mentor groups of 20 students, and so it's hard to do one-on-one interactions with 20 students, but students have to be really independent and motivated. But those students who are really independent and motivated have been very successful in this REU. Okay, so what did we prove in the summer of 2023? We proved that the number of Alexander polynomials with a ribbon number up to 4 is 56. And I will just say these are very effective at tabulating low crossing or ribbon numbers for low crossing knots. The Alexander polynomial is it's the right level of focus for this question. It's blurry enough that it doesn't see all of these band combinatorics, but it's fine enough that it gives us all the information we want. So I think we found the ribbon numbers of every knot up through 11 crossings except for 3 of them, and we found most of the ribbon numbers of 12 crossing non-alternating knots, but we did need this to get to the 12 crossing. Alternating knots, for whatever reason, are more difficult. We only were able to give ribbon numbers for about half of those, and we found bounds for the other half. Okay, that is the story of ribbon numbers of knots, but I want to tell a separate part of this story in my remaining time. And so one question is, what about links? And you might say, well, there's a multivariable Alexander polynomial for links. Presumably, we could do something there. If I'm being totally honest, we didn't try very hard. And so I think this would be a great project for someone to take what we've done with Alexander polynomials and convert it to the link setting. But you know, for the purposes of this talk, a link L is ribbon if L bounds a ribbon surface S consisting of L disks. So every component of the link bounds a ribbon disk, and in addition, those ribbon disks can have ribbon intersections with each other. So there would be like some multi-component disk band presentation here. In some sources, people would call this strongly ribbon, but we will just call this ribbon. And so you can define the ribbon number of a link similarly and try to minimize this and look for lower bounds. And we found an interesting bound coming from the Jones polynomial. And so so let's see. I am going to assume familiarity with the Kaufman bracket. I'm not going to explain the Kaufman bracket to folks at a Kaufman birthday conference. Again, I would if I had more time, but suffice it to say, it's a bracket that allows you to compute the Jones polynomial if you take the writhe into account. It's a formula for reducing a knot to constituent pieces and then working your way back. A nice combinatorial definition of the Jones polynomial. What I will show you is a picture that I lifted from a paper of Iserman, who was looking at the connections between the Jones polynomial and ribbon links in 2009. So I love this picture. I've stared at this picture a lot. Let's see. Here it is. So it is the difference between evaluating the Kaufman bracket around a ribbon intersection and the same picture where the ribbon intersection, two of the crossings has been changed. So instead of like a band passing through a disk, it's just two things that are flying by each other but not interacting at all. There's no immersion here. And the differences, well, you can see right here, this expression, and the surface survives in this way. And so Iserman used this to prove, I think, a rather remarkable theorem. So this is a theorem of Iserman. Which says that if L bounds a ribbon surface of S, let's say it like this, with the Euler characteristic of S equal to N, which is something that's larger than 0. So you can think like a bunch of disks. Of course, N ribbon disks will have Euler characteristic N. But it doesn't have to be disks. It could be like a disk and some annuli. It just has to be some ribbon surface. But the total Euler characteristic of all the components is bigger than 0. Okay, then we get that, let's see, Q plus Q to the -1 to the N minus 1 divides the Jones polynomial in the variable Q. So this is the Jones polynomial of the unknot, or the unlink, excuse me. Jones polynomial of N component unlink. And so one way to think about this is there's this nice cobordism from your ribbon link to an N component unlink, and then there's divisibility at the level of the Jones polynomial. What I want to think about instead is how the Kaufman bracket works with this. And so another way to say this is that negative a squared minus a to the -2 raised to the n minus 1 power. This is the substitution that you can go between the variable a and the variable q. This divides the Kaufman bracket polynomial of D, where D is a diagram for L. Those of you who know the story, like this, the Kaufman bracket is not quite a knot invariant because you have to normalize by the writhe. But if you're talking about divisibility, it doesn't really matter. And so then Iserman used this to define what he called the Jones determinant. So the Jones determinant of a link, of, let's say, such a link. So in order to define a Jones determinant, you have to bound a ribbon surface with Euler characteristic n. It's a way of getting at something that's like the determinant when the determinant vanishes. So it is determinant sub n v sub L. It is simply equal to, you take the Jones polynomial of the link, and then you normalize out by taking away this factor. The theorem says it's divisible by this, and then we evaluate at Q equals, is it I? I can't remember if it's I or -1. Anyway, it's an evaluation of Q What I have written in my notes is the evaluation at A. So let me just put that so I don't say something wrong. Negative e to the pi I over 4. So this is some number. The determinant vanishes because the determinant is the valuation of Jones' polynomial, but once you divide out by this factor, then you can get some number which may have some meaning. Okay, so what we have, I'm not going to show it to you because I'm going to run out of time. But let me state a theorem and then I will wave my hands at it. So using Eiserman's picture with the Kaufman bracket and the relation here between having a ribbon intersection and not having a ribbon intersection. So this is a theorem that back to Philippe and Stefan and I proved in this 2024 paper, is that the Jones determinant in absolute value is a lower bound for 9 raised to the ribbon number of the link. And the idea, the proof idea, it's very simple. It's an induction on the ribbon number. And so maybe I'll put this picture in here one more time. So we take this picture, we take the absolute value of everything and we evaluate at A equals negative e to the e to the pi negative I pi over 4. And so this is like, think of this as giving us, this is the knot L right here we find a ribbon intersection of L. This is smaller ribbon number. And so our evaluation, we can appeal to the induction. So smaller R. This picture for both of these have larger Euler characteristic. It goes up by 1, and so Eiserman's theorem says we have an extra factor that that vanishes. So these vanish, and then these two pictures have smaller r, and these two pictures have smaller r. And so we end up being able to show that the ribbon number of, well, in any case, maybe I don't want to say something confusing or wrong. So what I will say is that once we plug everything in, we get a factor of 9 popping out, and we simply use the induction. 9 to the r sub L minus 1, maybe I'll write that. 9 to the r sub L minus 1 times 9 is equal to 9 to the r sub L. That's what this all boils down to. But I've already gone 2 minutes over time. And so I will say happy birthday to Luke Hoffman, and thank you very much for your attention.